Yeah. So let's take a look at the reader-writer lock, and that is an approach that is that is also kind of useful to know because you're using semaphores or condition variables, and you want to implement like sometimes a special version of a lock. So let's take a look what a reader-writer lock is. So the main idea is that you want to reduce the contention when reading shared data. Because remember, reading doesn't cause a problem itself. So if two threads are reading the same data, that is not an issue. The issue arises when one thread is writing and other threads are reading. So, we can potentially have like 100, thousands, whatever, threads reading data simultaneously. There is no issue with that. But the moment that at least one thread modifies this data, that we have to do something about it, right? So, and definitely multiple threads cannot modify this data simultaneously. Only one thread typically needs to do that at a time due to mutual exclusion. So, so basically the idea is, so the reader-writer lock, we want to allow any number of threads to simultaneously read data, and only one writer can modify the data at a time. So either multiple readers, any number of readers can read data, or like a mutual exclusion, one writer is writing data. One and only one writer is writing this data, right? So other writers have to wait. So basically, what it allow? It allows n reader threads, 0 writer threads, or 0 reader threads and 1 writer thread. That is the idea of a reader-writer lock. So why is it useful? Well, because multiple readers can read simultaneously, and that will increase parallelism. So they will no longer need to have mutual exclusion, right, compared to regular mutex. So, but the disadvantage of this approach is quite kind of complex, right? So, and it also, depending on use case, sometimes implementing this lock, because it has overheads, it will be slower, right? If it's a really small critical section, maybe it's not worthwhile to do that. So there are different variants of reader-writer locks. So there's one variant is reader preferred. So writer only allowed when there are no readers. So writers can be starved. So that means, let's say if there is why writers can be starved. Well, imagine a situation when one reader comes, then another reader comes. Maybe these readers are done, but in the meantime, just before at least one of them done, third reader arrives. So, and there's always some stream of readers, and we basically don't give a chance to a writer to write new data. So that means the writers will be starved. So they can be also writer preferred. So reader only allowed when no waiting writers. So let's say the moment the first writer comes, we want to say, okay, no longer we're going to accept any additional readers, so we're going to complete whatever we have right now, and that's it. But then readers can be starved also. So that's the opposite problem. So also you can have some sort of order preferred. So threads ordered according to lock acquisition. So if a writer comes first, then okay, we have to accommodate writer. If the reader comes first, we have to accommodate this reader, and so on. So ideally, it can be starvation free, but the more conditions we put on top of a regular like mutex, the more complex it becomes, and at some point it may be just not worthwhile to implement it, especially if it's a small critical section. So it's always a trade-off. what we actually want to achieve. So yeah, so how do we protect data structures using reader-writer lock? So now we have two kind of locks, rlock and runlock. That's for the reader side, and wlock and wunlock for the writer side. So yeah, so fundamentally from the API perspective, if we want to do some lookup in a hash table or maybe search in some linked list, doesn't really matter, right? So we will use reader lock and reader unlock. So remember that just because you have rlock for one reader, that doesn't prevent the second reader to get rlock also. So that means the second reader will not be blocked in rlock. So they will simultaneously perform hash table lookup. So now if we want to have the writing operation, a writer can do hash table insert. Obviously, we cannot do lookup at that moment, or we cannot insert another element at that moment. So writer lock implies that all other readers are blocked right now. So let's see how we can implement it using condition variables. And it's also, it should be also straightforward with semaphores, but let's look at condition variables. So we have the number of readers, so that will be a variable, and initially it's 0. So then we will also have a mutex, and we will have a condition variable, which will say that there are no readers. So that will be, signaled, this condition variable will be signaled when there are no readers remain. So now we have reader and writer. So let's see what will happen with reader and writer. Let's take a look at the reader side first. So we have a mutex, and just for a second, assume that whenever the writer is active, you will hold this mutex. So you will hold this lock mutex, right? Lock M. So that means no reader can grab the lock in this very first line of this loop, unless the writer releases this lock. But let's say the moment the writer releases this lock, this mutex will be available. So let's assume that it's available. So then the corresponding reader will be able to grab this lock, and we'll go further. So going further means incrementing n readers by 1 and then unlocking this mutex. So it will not hold this mutex. So but the n readers will be incremented before it unlocks. So now it will go to this read critical section where multiple readers can proceed. So you can see that multiple readers can come because the only thing that they need to do to grab temporarily this mutex, to increment this variable, and then they can immediately proceed to the read critical section. So assume that read is much larger, right, than incrementing or decrementing something, right? I mean, this is like, we assume that this is a really small critical section compared to the read critical section. Yeah, so then after this, what are we going to do? You're going to grab this mutex again. You're going to decrement n readers. So you'll say that I have one less reader now. And if there are no readers remain, you are the last reader. You wanna wake up the writer, and I will get to the writer in a moment. And using the const signal, and basically that will wake up using this condition variable. And then finally you unlock the mutex. Remember that it's better to do const signal while it's still holding the lock, right? So while it's still holding the mutex. Unlike semaphore post it's not really related to any mutex. As condition variables, we have some mutex that is always associated with the condition variable. So technically, for example, for project, only for select you need to, I think, hold lock while you're doing sem post. so that you are protecting from deleting it from the list. But in general, when you do some post, it's not needed. Yeah, but const signal is recommended to always hold the murex. Just remember that it's not always required, but in some cases it is required. In some systems it's required, like NetBSD is requiring to do that. But POSIX, just recommends to hold the lock. Okay, and then finally it will do other things, right? So other things means outside of the critical section. So what did we do fundamentally? We grabbed the lock to increment the counter. So that was a very short critical section. Yeah, that requires mutual exclusion, but that's a very short critical section that all readers will perform. And then the most important, part is the read operation. So that all readers can perform simultaneously, because you see none of them is holding the mutex, right? So all these readers will be able to proceed without holding the mutex. And then, at the end, we grab the mutex again, just to decrement the and readers count and signal. If I'm the last thread, I will signal the writer that I'm the last thread, you can proceed now. And then we unlock the mutex. So let's take a look at the writer. So in writer, what we will have, the first thing that we will do, we grab the mutex. If we are not able to grab the mutex, that means the readers are modifying it right now. So they will increment or decrement counter. But assuming that I was able to grab the mutex, so at that point, I can check how many readers are currently in the critical section. So remember that you can only change and readers while you hold the lock. So readers will have to grab the mutex before changing n readers variable. So therefore there is no data race here. So because we are holding the lock, we can now check n readers. So while n readers is 0, remember that for condition variable we have to do this while loop rather than just one check if, right? So while less than readers greater than 0, so we will do cond wait. So we will say, okay, there is some readers there. Let me block and wait until all readers exit the critical section. So when n readers becomes 0 again. So the moment n readers is at least 1, writer is going to be blocked due to cond wait. So what does cond wait do? Remember that cond wait unlocks the mutex internally, then sleeps, and then when it wakes up, it will lock the mutex again. So that's like 3 operations combined together inside, right? So therefore it will sleep, but before it goes to sleep, it will unlock the mutex. So just remember that. So that means readers can really go ahead and modify this and readers. For example, reader when it exits, it has to subtract n readers, and then you see when n readers become 0, then at that point we will have cond signal. So that will wake up cond wait, right? Cond signal will wake up cond wait. So, but let's say I was able to I was able to get to the condition when n readers is 0. Recall that when n readers is 0, I'm also holding the lock already, because cond wait internal, as I said, this is unlock, sleep, and lock, right? So that means it was able to grab the lock, and after it grabbed the lock, it makes sure that n readers was 0, because it's a while loop. So that means the only condition to break from this loop is when n readers become 0. So I have a lock, and I know for sure that n readers is 0. So only after this, I can proceed and do this right critical section. What will happen to other readers? They will block. So they will block on the very first line of the while loop. They will try to grab the mutex, but they are unable to do that because the writer is currently holding the mutex. So the writer, unlike readers, will not release the mutex until it's done with the critical section. So the writer will only release it after the write operation. So now readers are coming, They're trying to grab this lock M, but they're unable to do that. So they cannot increment on readers. So only when writer is done, they can finally grab the lock again and increment on readers from 0 to 1 and 2 and so on. So the moment it becomes 0, and readers become 0, now writer is in control very much, right? So so we can go back to the writer, and we can, the writer holds the mutex and doesn't allow anyone else to grab this mutex. So does it make sense? Yeah, so this is how we can implement how we can implement the reader writer lock. So just a question, because it's like related to the project also. Why do we need to have a while loop rather than just if for cond wait? Okay, go ahead. Yeah, but what may happen, right? So let's say, okay, for the first iteration, first iteration is obvious that we need to check, because if an readers is already 0, we are done, right? So the writer, that means no readers, we can immediately proceed because we already hold the mutex. So the first iteration is clear. So why can we wake up and still n readers is not 0? So let's say let's say I did cond wait, but the assumption here is that potential I can sleep and wake up, and then readers is still not 0. Well, remember that cond signal will notify us, right? But we didn't get the mutex yet in cond wait. Remember that internally it sleeps, and then we'll only get a log. It has to get a log still again, right? And then only after this it will check n readers. But imagine that we have sent cond signal, so we are kind of said, okay, writer, you can wake up, but somehow maybe the scheduler was behaving such that we unlock this mutex and another reader was scheduled right after this. And the other reader right after this immediately grab the lock, increment and readers. So by the moment the writer wakes up and gets this lock again, so it will see that readers is already not 0. Does it make sense? So yeah, so it's so we cond signal is not going to wait until the writer wakes up. It will just basically going to mark the writer and say, writer, please wake up. So when it will exactly happen, that depends, right? So it may happen right away, like after you unlock the mutex, or it may happen a little bit later, right? So it just basically moves the writer from the blocked queue to the ready queue, right? Fundamentally. So this thread is now ready to be executed. But the problem is that while you're doing this, other threads are still computing for the same mutex, just like this writer, and they can still potentially change n readers. So another reader can change n readers. So does it make sense? Yeah, so be careful when you use condition variables. So this is why with condition variables, you typically have some sort of while loop, because you can wake up and the condition can already change. So just make sure you understand that. So it's potentially possible that you have a spurious wake up, so to say, right? Yeah, so make sure you understand that part. So unlike semaphores where everything is kind of precise, when I do sem post, it increments semaphore, it unblocks the sem wait and so on, right? So, but here it's kind of a little bit imprecise, right? So we just have signal can be lost if it arrived before the corresponding cond wait. That's one condition, and the other thing, that condition can actually also change. What is your question?
If you have a writer in the while loop and it has the mutex locked, and you had
But it doesn't have the mutex locked while it's in the while loop, because the moment it calls conwait, it releases mutex, then sleeping and then grabbing the mutex again, right? So like three operations inside this one operations.
Okay.
So logically, just view it as a free operation: unlock, sleeping, and lock.
So this would be an example of reader preferred.
Well, this one, yes. So writers can starve. Yes. So writers can definitely starve. You know, especially as I told you, right? The moment you can do quant signal, you even signal the writer that it's ready, but then another reader comes and grabs this mutex right away, and you know, it's the writer doesn't even have a chance to get to this writer critical section, and not to mention that readers can just come and never even create a condition when unreaders is zero. So the moment unreaders becomes greater than zero, writer can never have a chance to do anything, right? So because it's basically one reader, another reader comes, another reader, and that's all, right? Yeah, so this is so this is precisely problem is this implementation that writers can start. Any other questions? Yeah, just a reminder regarding academic integrity for project free. Yeah, please make sure don't violate any rules, right? So we are watching at your repositories, and by the way, we are actually using automatic tools to detect violations specific for project one. I already mentioned that. I think there was some violations, so there will be, but not too many, but there were some violations. So just so just make sure you don't. I mean, again, there is no need to, because the moment you do any violation, that can really drag your grade to like D and F, right? So and at that point, it's really bad. So it's better not to. It's better to get a lower grade than to get in this condition, right? So yeah, so basically also you already have pretty good material, right? So these lectures we have produced and consumer, so it's really straightforward to implement a basic version. So we just basically, as I said, I think we have 80% of the answer on the slide already for produce and consumer. It's just one condition, but you have two conditions like empty and full, right? So, but it's pretty much similar. Whether you use condition variables or use semaphores, that should be straightforward. And for semaphores, I gave you a hint how to implement close. That puts you a little more than the basic version already. And then finally, you can implement select. So just wanted to remind you how we can implement close. So we already talked about this, but just want to kind of put it in a slide so that you remember that. So remember what was the problem with close. I guess with condition variable, there is no problem because you can just broadcast and that will wake up all waiting threads. And at that point, you can check that the channel is closed. With semaphores, we don't have opportunity to broadcast. We can only wake up one thread at a time. I mean, unless we want to do something hacky, like do some post in a while loop, but that's not a good thing, right? So what we're gonna do is, so what is the problem? So when closing channel, we need to wake up all threads, right, that are currently blocked, but use this channel. So we do just some post for one receiver and one post for one sender. So in the close operation, you do some post for on the receiver semaphore, whatever you call send semaphore. You may call the semaphores differently, right? So this is for the full and empty conditions, right? So basically, you'll block one thread at that point. That thread will wake up if there was already one thread. If there is no thread waiting, sender or receiver, that will go for the future thread that will come in the future. Remember that same post is kind of sticky, right? So it doesn't go away. so you basically poke one thread for the receiver and one thread for the sender. But these threads will they will check that the channel is closed and will return, of course, with an error at that point. But before they do so, they will have to also propagate this news, right? So they will have to do some post on the sender, will poke another thread, a receiver will poke another receiver thread, and so on. So they will do some post on that. So it's like domino effect. So kind of push one domino, right? So and then everything falls down, right? Yeah. So so for the only node maybe for some try wait. So remember that some try wait, when it succeeds, it's exactly the same path as some wait for non-blocking, right? So for non-blocking versions, you will use some try wait. So that's exactly the same path as some wait. So there is when it succeeds. So there is nothing special there. But when it fails, remember that when it fails, it also doesn't change the semaphore value. Therefore, it doesn't need to participate in this, in this chain reaction, so to say, right? So it doesn't need to propagate this news. It's basically analogous to just hearing the news, right? Okay, the channel is closed, but you are not even in the line for that channel, right? So you don't need to propagate this news. There is no obligation for that. Yeah, so that thread can just leave, if it fails for some try wait. The only thing that you probably still want to clarify what the error is, whether it's closed error or would block. And that is particularly, I think, important for select. I'm not sure whether the tests will check it directly for a close or for not blocking operations, but for select, it may be important to know when the channel is closed. So therefore, even though it fails, but if the channel is closed, then there is no point in returning would block. You can return closed error at that point. But again, if it fails, you don't need to participate in this chain reaction. It means you just heard the news from you overheard this news that the channel is closed and basically return, right? So you're not in the line. So that's just to remind how you can do close. So I think close is pretty straightforward. And to be honest, both semaphores and condition variables should be straightforward. I guess for condition variables, don't forget that you will have to have this while loop, and for condition variables, you also don't have anything like some try wait. But for condition variables, because it's not really kind of precise in terms of notifications, so that means you will just check whether the buffer is full or empty. So that should be straightforward. But for semaphores, it should be precise, and I'm also emphasizing this, right? Your semaphore value should be in sync with the buffer size, with the buffer, how many elements you have in the buffer for full condition. Yeah, sorry, yes. It should be precise in terms of how many elements you have, right, in the buffer, right? So initially, you initialize, let's say, the sender semaphore on how many slots you have available in the buffer initially, right? So that should be in sync. The semaphore value should be in sync with that, and the receiver should also be in sync in terms of the moment you send one element, the receiver, you do some post, right? So the receiver semaphore will also reflect how many elements you have in the buffer right now. So that should not go out of sync. Yeah, so this is why you want to use some try wait for the non-blocking version, because you still need to modify the semaphore value. Yeah, so and for condition variables, as I said, but it's not that precise, but then you still have this while loop to mitigate the same issue. Okay, so also select, right? So for select, I covered that in the past. Just please watch video recordings for lecture 24, 25, I think. and others also. That in general has some hints for channel close and channel select. So just also a reminder for like kind of what kind of protocol would be recommended for channel select. So you will have a local semaphore for each select operation, because you cannot block on any of the channel condition variables or semaphores. So you will have this local variable. You initialize it, you register it with all channels that participate in the select operation. So for each channel, you'll have a linked list, I guess, for receivers and senders. There will be two different lists. So insert a pointer to the semaphore to this list. So for that, you also need to implement the linked list, like double linked list in linked list.c. So then you effectively so only after you registered semaphore, then you will do a loop. You will perform non-blocking receive and send, right? So you don't want to block on any semaphores or condition variables. So if any of this operation succeeds, fine, you are done, you exit. But before you exit, of course, you're going to unregister semaphore and so on. But if you are not done, everything fails, and the channel is not closed, so you would block on the same wait, right? So you would block on the same wait, and if nothing is successful, repeat the loop when some wait wakes up, right? So remember that the semaphore is now registered. So the second time you check, you either was like notified the reason why some wait wakes up is because somebody called some post. But it's possible that another select grabbed that channel, because there was maybe another select that was using the same channel already grabbed this notification, so that you kind of have a spurious wake up. So of course you need to go through this loop again, and maybe two channels have something ready, right? So maybe more channels have something ready. You just need one operation. So the only thing to, I guess, a little bit kind of minor note. That same weight can potentially be greater than one, right? So because let's say maybe multiple channels notify you. I mean, I don't think it's a very likely scenario, but because you typically, the moment you get the first notification, you already kind of fall through. But multiple channels can do some post on the same semaphore. So you kind of need to zero out semaphore ideally, right? So that you will avoid spurious wake up on the second iteration and so on. So how can you do that? Well, I did it just by basically calling. I mean, you cannot do some init, and you don't want to unregister the semaphore either. So the way that I did it, I just had a while loop for some try wait. So remember, some try wait will immediately succeed. It will not block until it reaches zero. So and when it's zero, it will return an error, right? So that it will say it would block. So I would kind of do a while loop in some try wait to reset semaphore value back to zero before going to the second iteration. Does it make sense? Yeah, so it's not, I mean, again, it's not, I think it will work and probably will pass tests without this. I just did it for like, so that I don't have any spurious wake ups, right? So because to reduce this overhead, because potential multiple sem posts can come from multiple channels. So it may be a good idea to reset the value to zero, but again, you cannot use sem init again, right? So so the moment the semaphore is initialized, you cannot change that value. So how can you do that before the how can you how can you reset the semaphore to zero to the original state if you need to block second time or third time or so on, right? So that you can do in some try wait in while loop. You want to do try wait so that it will not block. So finally, you unregister the semaphore from all list. So that will, that is important, right? Because otherwise somebody can do some post on the semaphore that was existed for the select, but remember that semaphore only exists for the duration of select. The moment select is done, you will call sem destroy, and this semaphore will disappear. So we want to make sure that this semaphore is unregistered from all lists before you call sem destroy. So in this particular case, I also mentioned last time that you want to do some post on the other side while holding the lock, so that this side cannot unregister the semaphore. So that's to avoid this race condition, because otherwise you may unregister the semaphore while the other side is doing some post. So yeah, and then you can have concurrent sem destroy and sem post. That would be bad. So because the only things that's holding back sem destroy is unregistered the semaphore. So you want to make sure you do that in the correct order. So also the order is important to avoid race conditions, right? So this is why we register first. Only after this we check. Only after this we perform non-blocking operations. Any questions about select? Okay. Again, we have some video recordings, and this is just to kind of summarize what we had there. So also I wanted to mention, I think that was a while ago, but just wanted to remind you, so there is SEQ teaching evaluation. I think it's the same as was formerly known as SRTE evaluation. Yes, so but I noticed there is some difference that it ends sooner than in previous semester. So it will end, I think, on December 3rd, if I'm not mistaken. Please double check that. Yeah, so it will end sooner. So I think pretty much this week. So yeah, so I will give, I mean, typically with the way I do that, and university policy allows that, right? So specifically, I think on their website, they say they can do that. So I give small credit for completing the evaluation to everyone, right? So typically when we reach like 80% or something, let's put 80% as the goal, target goal. Yeah, so then I will give credit to everyone. That's a small credit, of course, right? Not a big deal, right? So, but still, yeah. So anyway, so just for your effort, right? Yeah. So anyway, so let's just wanted to remind, in case if you haven't seen that. Yeah, I think also for some reason for section 2 they didn't show me as an instructor, but I guess everyone here is section 1, but that should be for section 1. I think it was fine, but that I think was fixed. But just wanted to, just in case, to let you know that, because may not have appeared before.
I can confirm you're on there.
Okay. Okay. Yeah, I think for section 1 there was no issue. Okay. So yeah, so we will any questions about concurrency and project free? Yeah, so I think we covered some topics, and we looked at condition variables like reader writer locks also today, how you can use condition variables, just another example of that aside from producer consumer. And for semaphores we looked at different problems as well. Hopefully that will be useful for your project. Yeah, so again, for basic version, I mean, I shouldn't say basic version. For send and receive, you can use condition variables or semaphores. Just be consistent. If you use for one side condition variables, then use condition variable for the other side, because otherwise it will be very good. I guess it's also possible to have a mix, but there is no point in doing that. But just be consistent. Use either two condition variables and murex, or two semaphores and murex. You can solve this close operation with both approaches, so that should be fine. Non-blocking is also fine with both. For select, I recommend you to use a semaphore for this local as a local variable. So you'll probably want to create a couple of more mutexes, though you can probably still use that original mutex as well. That's fine. Like for receiver list and for sender list, you may want to create separate mutexes, or maybe create just one mutex for them. It doesn't matter, right? I mean, ideally you want to do as fine grained as possible, so having separate logs, as long as you don't have any race condition, is fine. But you can also go. You can probably also go with one log. Yes, so that is just to, that's not to say that you cannot do it with condition variables. I think you can do it with condition variables as well, but I would just do that with semaphores because it's probably easier. Yeah, but with condition variables, it's a little bit tricky sometimes because you also have to have a mutex associated with this condition variable. And then you have to store it. Maybe you have to pass a pointer to a struct which has condition variable mutex, so it may be a little bit tricky. But I think that it's possible with both, but I would recommend to use semaphores for select. And for extra credit, only do that if you have time. So just but it's still maybe nice to try it, at least maybe not fully completed, but at least some tests, so that you pass some tests or something like that. Okay. So our next topic will be related to I/O and file systems and storage. So first we will start with just overall picture, what the overall OS big picture is. So remember that we have the system call interface. I mean, I guess what's above system call, that's not so interesting. Like this is libc, maybe other libraries, at least from the OS perspective, right? From the OS kernel perspective, there might be a lot of different libraries. You may run, really heavy applications, and that's fine, right? But when we consider OS kernel, that we are mostly considering this low level parts, right? That going to be below the system call interface. So remember that libc translates these calls to system calls. So eventually you're going to reach, let's say, the OS kernel, like Linux kernel, and you have different, subsystems inside the OS kernel, because typically, like if you deal with multi-kernel, such as Linux kernel, has a lot of things going on inside the OS kernel, like Windows, OS X, doesn't matter, right? So they still have pretty large kernels and have a lot of stuff going on there. So you're going to have IO subsystem, memory management subsystem, process management subsystem. It may be called differently in different operating systems, but fundamentally that's what you have. So for memory management subsystem, remember that you have this virtual memory support fundamentally, like page replacement algorithms and so on, right? So to take care of this, to make sure that we can evict some pages and print some other pages. It also has page cache, which I will talk about. This is to help you with, to cache in some, I guess one side is from virtual memory perspective. On the one hand, you want to be able to use secondary storage to basically push whatever like memory you cannot fit in physical memory, right? So you wanna put it on the secondary storage. But there is another problem. Maybe you have a lot of memory available, and you have really slow devices like hard disk, because even if you use SSD, that's still slower than RAM, right? So you wanna maybe you access some files like many times, right? So you wanna make sure you kind of cache it also in memory. So the opposite is also true. So when you have a lot of physical RAM, you wanna kind of keep the stuff cached inside memory. So, but this is also kind of tightly integrated. So how much stuff you want to do that in this, like sometimes you want to actually evict pages for, let's say you're running some executable file. So that's actually one of this misconceptions that you don't need page replacements or like swap area anymore, right? Because you have a lot of memory. Well, that's not fully true because when you have more RAM, you can use it more efficiently. Let's say you run some executable file, and in that executable file, there are some pages which I use just once, or maybe used very rarely, right? On the other hand, there are some files that you access on your disk, over and over again. So they're actually stored on the disk, but you want to cache them in memory because you're gonna run them over and over, like you're gonna access them over and over again. So sometimes you want to actually evict some pages, like some from executable files or whatever, right? So whatever you allocated in memory to the swap area, and also cache something in your RAM, right? So because that eventually can be more effective strategy. Because if this file is accessed over and over again, it's better to keep it in RAM and evict some page that is just was used once and that's it, right? So therefore, it's not necessarily true that nowadays we don't need page replacement algorithms or don't need swap area because we still need both, right? So we still need sometimes caching files in RAM, and that makes your system faster. Okay, so then you also have process management subsystem. You can create processes, threads. Remember that we also talked about some scheduling algorithms, right? So some schedules, preemptive and non-preemptive schedulers. I mean, yes, technically speaking, I guess for modern operating systems such as Linux, it will be a preemptive scheduler. So there will be even more stuff, like some tasks will have higher priority than others and so on. So it will also have signal handling. So that's kind of mechanism. I guess you probably have covered that in 3.11. That was some sort of notification mechanism that you can use in user space, similar to interrupts in kernel space, right? So we can have some sort of software mechanisms to in user space that are implemented in operating systems. So that's at least how you can use signals. So that's like OS or software versions of user space interrupts, so to say. Yeah, so, and then you have IS subsystem, right? So this is something that we are going to talk now, right? So there is a virtual file system, the so-called virtual file system. So it's not a true file system in the sense that, it's not like a separate file system that you have on your disk, but it's just a layer in the operating system that allows you to talk to multiple file systems, to multiple, to different devices. So for example, you can view your entire hard disk as a one large file also, right? So that's also a possibility, right? There's different ways to to treat your devices, right? So, in Linux or in Unix in general, there's kind of a concept that everything is a file, right? So everything is treated as a file. Your partition treated as a file, your entire storage device treated as a file, even your terminal is a file. Everything is a file. So and then there is some components like sockets, network protocols, file systems. If we're dealing with block devices, it's a general block device layer and so on. So that's just a high level picture. So let's take a look specifically at the device driver stack. So how does it translate from user mode to kernel mode and to hardware? So in application, you may have like calls such as open, read, write, close, and so on, right? So those are, I mean, those are also kind of low-level operation, I should say, right? So because you have fprintf, fwrite, or like maybe even higher level functions, right? But let's just assume that we are using this POSIX function to manipulate files. So how do they translate? Like we have a corresponding system calls, right? So this typically in Linux, there will be corresponding system calls for read and write operations. So through the VFS layer, eventually that's gonna reach a file system. So through this virtual file system layer, it will reach the specific file system implementation, maybe this ext4 file system that you have in Linux. So eventually, that's gonna reach the generic block interface. So that's going to be block read and write. So that's for block devices that we have, right? Oh, what was that? The previous slide. So that was generic block layer, right? That we had below file system. So then from this generic block layer, it has to access a specific block interface. So it can be, some SCSI device with ADIs, or maybe you have other, block, some more modern, block devices. So that will reach the device driver layer for that particular, protocol and so on, right? So that's typically done in kernel mode, at least in monolithic operating systems such as Linux. Yeah, so that will be, so you'll have the device driver running in kernel mode. And even a file system driver runs in kernel mode. So again, in Linux, everything is kind of treated as a file, right? So devices are also accessed as a special files. So you can even check, like go to /dev. So you will see a lot of weird files there, right? So that's basically designed for these devices, right? So we have special files for each device. So you can still use like regular open, read, and write operations through this like system caller. In fact, you can open like something like dev SDA or something like this, right? And treat your entire hard disk as a as a one large file. And then maybe you can even implement your file system in user space and have something implemented everything entirely in user space. So you can bypass kernel for that. Yeah, so but eventually it's going to be handled by device drivers at lower layers. So depending on what kind of file you're accessing. So yeah, if it's if it's partition, maybe it also has to go through this partition, not just the storage devices, but you also have some support for different kind of partitions. We have legacy partition like MBRG and modern GPT partitions and so on. Yes, so in general, you have two kind of devices: block devices and character devices, depending on what type, or device it is. So sometimes, for block devices, we typically access a large chunk of data. So just some examples. So like old style drivers, you can see like IDE drivers such as def, HDA, and HDB. I guess those you will not see unless probably use VMs, but like at least natively, it's unlikely that you will see nowadays for modern computers. So SATA like serial ATA or SCSI devices that will be probably that you can still see as DA, SDB, and so on. Also virtual drive, if you use some, virtual machines, you can see like VDA, VDB, and so on, right? Partitions within drive, so there's like def SD1, SD2, and so on. There's things like, I guess, parallel printer is also something very old, right? So, but there's still interface for that, LP0, LP1, and so on. So there is also special null device, dev null. Yeah, so I don't know, some people make jokes that all emails will be forwarded to dev null. That means it's like a device that, has zeros or like, nothing, right? Yeah, so actually I should say there is a difference, right? So there is zero device. That's when you want to initialize something as the input. So there is a difference, right? So you want to dev null is basically you redirect something to dev null, but sometimes you also want to initialize something, maybe some file with zeros. So you will use dev zero. So that will kind of take blocks initialized to zeros. Yeah, there is also random source device. Maybe you want to just generate something random. So there is dev view random device. So that's all. That's another example. Terminals, TTI1, TTI2, and so. There is pseudo terminal. I mean, there is some other devices. Of course, we will not cover them right now, right? So, but actually, even historically, there was some audio devices, like even your sound card and so on, right? So, but yeah, so there is a lot of different devices that you're gonna have, like even I think mouse, like that was also there, at least, but nowadays they're mostly USB mouses, so but that's a different story. Okay, so block and character devices. So for block devices, so first of all, block devices, right? So the idea here is that you typically want to have buffered device accessed, supporting random access. So that means I can access this block, and that block. On hard disk, it can translate, I want to access this sector or that sector on a hard disk and so on. But, we don't specify whether it's a sector or some other unit. I guess if for flash memory, it can be different units, right? So you don't view it as a physical sector. So it's a general term for this as a block. So you can view this as a buffered array of blocks, right? So like maybe a buffered array of 512 bytes, block of 512 bytes. Or maybe nowadays they have 4 kilobytes blocks and so on. By the way, don't confuse it with the file system block, because file system block can be larger than, the underlying block size on the physical device. I mean, you can have 4 kilobyte blocks in a file system and 512 bytes in a physical device. So examples as hard drives, RAM disks, CD-ROMs, all these kind of things, right? So that's that's a typical example of a block device interface. So character devices. So here you want to have unbuffered direct sequential access. So it's more like sequential. So it's not like random. I want to read that block or that block or that block. So it's more like sequential access. So it's effectively kind of like a stream of bytes. Examples for that, like keyboard, mouse, like serial port, and so on, right? So when you type something on keyboard, it's not like, doesn't really make sense, access that block or that block, right? Because you have like a stream of bytes. So it's a different kind of device. Yeah, so you can identify these devices by major and minor numbers. I'm gonna probably skip that part, but that typically you in each device driver you can you can specify this major number, just kind of a minor note. Yeah, so let me also kind of, yeah, what time? Yeah, okay. Let me still have a little bit of time. So let me just kind of connect what we had, like Linux storage stack. Yeah, so for Linux storage stack, right? So whatever we have in the kernel space. So how can we kind of translate it or expand it, right? So for an application, we have this calls like open, like read, write. So that will go through the VFS layer. So I guess it's pretty small here, right? But hopefully you will have the slides. Yeah, let me see if I can make it. Yeah, but I can read it. Okay, so then it reaches the VFS layer. So there you can, for example, have block file systems such as ext4 or maybe ISO 9660 like used for CD-ROMs or maybe DVDs. So then you can have or sometimes maybe network file system like NFS or something like that, right? So that's going to be VFS layer will transparently connect us to this file system. So remember, I also mentioned page cache. So this is something that you would kind of, when you access these files, you want to cache some data in memory, and that's part of the memory management subsystem. Because you want to know how much memory you have, right? And what kind of memory you can recycle. So basically any unused memory can be used for caching these files pretty much, right? So for that purpose, you're going to use page cache. So that's just basically caching these blocks that you are accessing all the time. But like what kind of strategy you can use, it's a different story. Like you can use LRU here, like least recently used. And for blocks, that's fine, right? So that's not like for page replacement algorithm. So for, I guess, for block devices, it's okay. So that we can use, we don't need to approximate like log algorithm or anything like this. So we can use, more something closer to the optimal algorithm. So we still cannot use optimal algorithms, but we can use our U at least. Yeah, so then it reaches the block layer, block I layer, so then eventually that's going to go to this specific layer, right? So for example, you can go to SCSI layer, right? So then SCSI will have also different layers like upper layer, middle layer, lower layer, and so on, right? So there is that, and eventually you're gonna reach the hardware like part, right? So you wanna reach to talk to the actual hardware for the specific registers and so on. So that's like how long it takes when you write to some file. You see how many layers it will have to go through. Okay, go ahead.
So on the right, we have the hooked in device drivers like NVMe drivers. Do those not go through a scheduler? Because it looks like that branches off before the IO schedule.
Yeah, so that's a good question. Yeah, I think this one, yeah, so I need to actually double check for NVMe specifically, but I think that should be correct. Because NVMe is somewhat different. It's not the same as it's not exactly the same as legacy drivers such as SATA or something like this, right? So that's completely new driver, right? So completely kind of different driver, right? So even if you have like SSD basically based on an NVMe interface, that uses completely different layers in the Linux kernel. So it's completely different driver, right? So like when you use SSD for SATA, that's different. Yeah, so one reason also is because that's kind of directly connected to this PCIe bus, right? So you have this kind of you don't need to go through that traditional block, not a block, but still go through block layer, but you don't need to go through this traditional SATA layer, right? So